So one of the major developments of the previous section is the idea of a matrix inverse. If we have a square matrix A, the inverse of that matrix is something you can multiply it by on either side in order to get the identity back as a result. Now this is actually a very powerful tool in linear algebra, but one of the limitations is that we don't always know what the inverse of a given matrix is, or if it even has one. In the case of a 2 by 2 matrix, we do have a formula for inverses, but beyond that, we don't yet have anything. And that's going to be the goal of this section, to answer the following question. So given an arbitrary matrix A, it would have to be square. How can we determine if A has an inverse, first of all, and if so, what is that inverse? Now it turns out that the tools we're going to need in order to answer this question are called elementary matrices, and that's what this section is about. So I just want to quickly remind you, what are these three things? What are these things? Interchanging two rows, add a multiple of one row to another, multiply a row by a non-zero constant. These have a name. Remember, they're called the elementary row operations. Now, why am I reminding you of this? Well, we're going to define something called an elementary matrix, and it's going to be tightly related to this idea. So this is a definition. You can see I've got a couple of blanks to fill in. This is kind of the style that I'll use for giving definitions in the future, just to cut down on some of the writing and make these videos a bit shorter. So an elementary matrix, what is it? An elementary matrix is a matrix which can be obtained from the identity matrix directly with only a single row operation. So exactly one of these operations. So I'll say single row operation. So anything you can get by starting with the identity and doing exactly one elementary row operation upon it, and then whatever your result is, or whatever you can get in that fashion, is called an elementary matrix. So let's look at a couple of examples. Here's a 3 by 3 matrix. I'm going to claim to you that this is an elementary matrix. And how would I justify that? Well, I'd have to be able to tell you how to obtain it from the identity matrix with a single row operation. Now, of course, we must be talking about the 3 by 3 identity matrix here, since this matrix is a 3 by 3 matrix. So ask yourself, what could you do to the 3 by 3 identity matrix? What single operation could you do to the 3 by 3 identity matrix? I mean, that would turn it into this matrix. Remember, the 3 by 3 identity matrix would just be very similar to this, but it would have ones all along the main diagonal. So if you multiply the first row by 3, you're going to obtain this. So that's the row operation that it corresponds to. Take row 1 and replace it with 3 row 1. And that is the elementary matrix. Pardon me, that's the elementary row operation that corresponds to this matrix. So that's, because there is such a single row operation, that's what it means for this to be an elementary matrix. What about this one? Now here's a 4 by 4 matrix. How could you obtain this from the 4 by 4 identity matrix with a single row operation? Well, this almost looks like the 4 by 4 identity matrix. There's only one thing different. Well, two things different. The first and second row are both in the wrong position. And in fact, they've traded places. Right? If this were the 4 by 4 identity matrix, we would actually have this as row 1, and we would have this as row 2. So actually, that's the operation. Switch the first and second row. So row 1 interchanges with row 2. That is the corresponding operation that verifies that this is an elementary matrix. Okay, and then one more example. Here's a 2 by 2 matrix. How could we get this from the 2 by 2 identity? Well, if you subtract the first row from the second row 4 times, that would do it, right? If I started with the 2 by 2 identity matrix and I did the operation row 2 is replaced with row 2 minus 4 row 1, then I would get exactly this matrix. If I perform, let me be clear, you would take this operation and you would not perform it on this matrix. You would take this operation and you'd perform it on the 2 by 2 identity matrix in order to get this matrix as a result. And because you can do that with a single row operation, that means this is also an elementary matrix. So in summary, all three of these matrices are elementary matrices. Okay, so that's the idea of an elementary matrix, but what you might be wondering at this point is, well, why should you care about it? Why should you care about elementary matrices? And this theorem is actually going to tell you why. So here's the theorem. If E is an elementary matrix which corresponds to a particular row operation, just like these, for example, these three elementary matrices corresponded to these elementary row operations. So every elementary matrix corresponds to a row operation because that's how they're defined, right? They're matrices that can be obtained from the identity matrix with a single row operation. So this single row operation is the row operation that they correspond to. So let's say we've got an elementary matrix E, it's got to correspond to some row operation. Well, what happens if you multiply some other matrix A, let's say, on the left by the matrix E? Well, what it's going to do is it's actually going to just perform that row operation on the matrix A. And that's the neat part. That's the cool part about elementary matrices. And really, it's a cool feature of matrix multiplication. It's designed to work this way. So how do you finish this off? So multiplication on the left by E has the effect of performing that operation. And that, again, that operation, I mean the row operation that corresponds to the elementary matrix E that you started with. Okay, if that doesn't quite make sense yet, let's look at a couple of examples and then come back and summarize, and we'll read it again. And after seeing a couple of examples, it makes a bit more sense. So in part A, look what we have here. We've got a 2 by 2, we've got a product, right, of a 2 by 2 matrix and a 2 by 3 matrix. So the result is going to be a 2 by 3. Right, so we know we're going to have a 2 by 3 product. And let's just perform the multiplication by definition, right? So the entry that goes in the first row, first column, I'm going to multiply row 1 by column 1. So I'll have 0 times 1, which is 0, plus 1 times 4. So I'm just going to get 4. Let's finish off the first row. So this entry is the first row, second column. So I'm going to go 0 times negative 1 plus 1 times 0. So that's going to be 0. And then for the third row and the third entry in the first row, I'm going to say row 1 over here times column 1 over here. So 0 times 7 plus 1 times 11 is going to give us 11. And now if I fill in the bottom row, I'm going to get 1 times 1 plus 0 times 4, which is 1. 1 times negative 1 plus 0 times 0, which that's going to give me negative 1. And then finally 1 times 7 plus 0 times 11. So that's going to give us 7. Okay, we just did that multiplication by definition. We didn't use the fact that our left factor was an elementary matrix. But this theorem says we could have, and it would have given us a shortcut. Because look what happened. Look at how the result compares to the factor on the right. It's the exact same entries, but just the first and second rows are interchanged. Right? And what row operation corresponds to this 2 by 2 matrix? This is a 2 by 2 elementary matrix, and it corresponds to exactly the operation of interchanging the first and second row. Right? So we could have made that observation right off the bat. Right? This is an elementary matrix which corresponds to interchanging the first and second row of the 2 by 2 identity matrix. So if we multiply this other matrix by our elementary matrix on the left, we're going to have the effect of interchanging those two rows. Okay, so that's the idea. Let's do part B and part C by actually using that feature of elementary matrices. Okay, we won't actually work these out from scratch. So we've got a 3 by 3 elementary matrix over here. And let's actually write down the row operations. And by that, I mean which ones they correspond to. So part A, the row operation that this elementary matrix corresponded to was interchange row 1 and row 2. For part B, in this example, what does this 3 by 3 matrix correspond to? Or what operation does this 3 by 3 elementary matrix correspond to? You can get this from the 3 by 3 identity by just multiplying the second row by negative 4. And that's why that negative 4 is there. So this corresponds to this operation. Take row 2 and multiply it by negative 4. Okay, so instead of actually working out this product by scratch, we know we're going to get, it's a 3 by 3 multiplied by a 3 by 2. The result is going to be a 3 by 2, and we could work it out entry by entry. But just use the fact that multiplying this matrix forming this product with this elementary matrix on the left is going to have the same effect as just simply performing this row operation on this matrix. So that's what we're going to do. Let's just multiply the second row of this matrix by negative 4. So we're going to get a 2 by 2 matrix. We're going to have 1, 0, oh, that should be a positive 4, negative 24, and then the third row won't change, 3 and 5. I don't normally write plus for a positive number, but I accidentally wrote a minus, so I just crossed it out to make it a plus. Okay, so that's what you're going to get if you multiply the second row of this matrix by 4, or by negative 4, and this product actually works out to be this by this theorem. All right, let's do one more example, and then we'll revisit the theorem one more time just to make sure that it actually says what we think it says. So down here in part C, what row operation does this 4 by 4 matrix correspond to? Well, if you had the 4 by 4 identity matrix and you did the following operation, and you said row 2 is going to be replaced with row 2 minus 2 row 4. So in other words, you took row 4 and subtracted it from row 2 twice. When you were working with the 4 by 4 identity matrix, you'd get exactly this matrix. So that means this is an elementary matrix that corresponds to this operation. So if you want to work this product out, just simply do this operation to this 4 by 1 matrix, and that will give you the result. So we're going to take row 2 and subtract row 4 twice. So take 1 and subtract 2 twice, because this is row 2 and this is row 4. There's really only one column, but so these are the rows. Those single entries are the rows. So we will subtract 2 from 1 twice and leave everything else the same. So we'll get negative 3, 0, and 2. Okay, so let's just revisit this one last time. So if E is an elementary matrix which corresponds to a particular row operation, just like this matrix corresponded to that row operation, this matrix corresponded to that row operation, and this matrix corresponded to that row operation, this matrix corresponded to that row operation, then if you just multiply some other matrix on the left by an elementary matrix E, you're just going to have the effect of performing that operation on whatever factor is written on the right, right? So this multiplication had the effect of doing that operation on this matrix. This multiplication had the effect of doing this operation on this matrix, and so on. You can see the pattern, right? So that's the idea of an elementary matrix, and the idea is we can use these to come up with a method for finding inverses of any square matrix. Or if they don't have them, then our method will find that out for us too.